Okay, you should have the paper in front of you right now. There are questions that go along with this. Yes, it's an old science video, but all the stuff that they're going to say is true and valid with our notes that we're currently doing right now. So you are going to watch the video, which I think it's like maybe 15 minutes. Answer the questions front and back. You can pause the video if you need to, and then you need to submit it today, Friday, January the 8th, on time, okay, to Blackboard. Alrighty. After the worksheet is due on Blackboard, then the answer key will come up under week folder 1. Okay, so under that folder week, you'll also see the answers, but it won't come up until after the due date. Alrighty, so here's the video. Let's go ahead and begin.
What makes one substance different from another? What makes the glass in these goblets different from the diamond in this ring? They are both clear, sparkling solids, but diamonds are one of the hardest materials on Earth and are even used to make saws which can cut rock. And glass is fragile, easily broken. The difference lies in the types of atoms that make them up. What makes atoms different from each other? We are going to take a look inside atoms and examine their atomic structure. Atomic structure refers to the arrangement and number of smaller particles of an atom. These smaller particles that make up atoms, or subatomic particles, include protons, neutrons, and electrons. Let us consider each subatomic particle separately. This is an atom of carbon, a substance found in charcoal and diamonds. The nucleus is the center or core of the atom. It is where 99.9% of an atom's weight is located. The nucleus contains protons, as seen here in red, and neutrons, seen here in green. Protons are positively charged particles, symbolized here by a plus sign. All protons are the same, no matter what type of atom they are in. The weight of subatomic particles is measured in units called atomic mass units. A proton weighs 1 atomic mass unit. There are millions and millions of protons in a single drop of water. The other subatomic particles located in the nucleus are neutrons. A neutron is a neutrally charged particle. They do not have a charge. Neutrons also have an atomic mass of about 1 atomic mass unit. While the nucleus contains most of the mass of an atom, it takes up only 1/100,000th of an atom's space, equivalent in ratio to this ball in this meadow. While all atoms have a nucleus, what is it that makes them different? The answer lies in their number of protons. The atomic number is the number of protons in an atom. For example, the element carbon, which is what makes up the graphite in this pencil, has an atomic number of 6. It has 6 protons. All atoms of carbon have the same atomic number of 6. The atomic number also equals the number of electrons. Therefore, carbon also has 6 electrons, seen here in red. Copper, a different element, has an atomic number of 20. It is useful to know the combined number of protons and neutrons in an atom. The atomic mass, also known as the atomic weight or mass number, is the sum weight of the protons and neutrons in an atom. Let's take the element silicon, symbolized by the letters Si. Silicon is a major element that makes up the sand on this beach. Silicon has 14 protons and 14 neutrons that add up to an atomic weight of 28 atomic mass units. While most types of carbon, such as that in these trees, have 6 protons, the number of neutrons may vary. Isotopes are atoms of the same element with different numbers of neutrons. For example, carbon can have an atomic mass of 12 or 14. Carbon with an atomic mass of 12, seen here with 6 red protons and 6 blue neutrons, is referred to as carbon-12. But carbon can also have an atomic mass of 14, called carbon-14, seen here with 6 red protons and 8 blue neutrons. Carbon-14 in nature is unstable and gradually deteriorates. With specialized equipment, scientists can estimate the age of objects, such as this bone, by measuring the degradation of carbon-14. Because most elements have more than one isotope, each element has an average atomic mass, calculated from the average mass of its isotopes. The fast-moving particles around the nucleus are electrons. Electrons are negatively charged particles. They are a fraction of the size of protons or neutrons. To help you visualize this size difference, if this ball were a neutron, then this P would be an electron. An electron weighs just 0.0006 atomic mass units. Because electrons weigh so little, their weight is not even considered in calculating an atom's atomic mass. The electrons move very quickly, perhaps as quickly as 1 billion times a second around the nucleus, forming what is called an electron cloud. The electron cloud is the space in which the extremely fast-moving electrons are likely to be found. As scientists learned more about elements and atoms, they developed a way to organize them in a logical manner. They created a chart to organize elements by their atomic structure that is referred to as the modern periodic table. The modern periodic table represents a remarkable scientific endeavor. It takes thousands of seemingly unrelated pieces of information and fits them together in a logical format. This organization is dictated by the periodic law, which states that both chemical and physical properties of elements are periodic functions of their atomic numbers. The position of elements on the periodic table is dictated by the number of protons, or their atomic number. Notice how the top number, the atomic number, increases from left to right. The elements on the periodic table are represented by their chemical symbols. A chemical symbol is an abbreviated way of symbolizing an element with 1 or 2 letters. For example, the element oxygen, found in the air we breathe, is symbolized by the letter O on the periodic table. Oxygen, along with hydrogen, is a fuel commonly used in rockets. Hydrogen is symbolized by the letter H, found in the upper left portion of the chart. Let's take a look at another element, calcium. Calcium is an element found in the human body and in the bones of other animals. Calcium is also common in rocks, such as limestone and marble seen here. It is located here on the periodic table. The chemical symbol for calcium is Ca. On top of the chemical symbol is the atomic number. The atomic number of calcium is 20. Remember that the atomic number is equal to the number of protons. Here you can see 20 protons with a positive charge in the nucleus. Below the chemical symbol for calcium is the atomic mass. Here you can see that the atomic mass of calcium is 40.08 atomic mass units. You'll notice that the periodic table is organized in a grid with rows and columns. There are 18 columns called groups or families. These groups or families have elements that possess many similar chemical and physical characteristics that we will explore later. The rows in the periodic table are called periods. Unlike the elements in families, the elements in periods do not have a great deal in common. But by looking at elements across the periods, we notice some interesting patterns. There are 7 periods or rows. Notice that a portion of rows 6 and 7 has been removed. These periods are still part of the periodic table, but have been moved to make the table shorter and easier to read. As you go from left to right in the periodic table, one obvious trait stands out. The atomic numbers increase in regular intervals. For example, you see how the atomic number increases starting with silicon with an atomic number of 14, then phosphorus with an atomic number of 15, then sulfur with an atomic number of 16, and so on. Of the 109 known elements, the vast majority are metals. These are highlighted on the periodic table in green. While you may think of objects such as silverware, pans, and wires as metals, other elements, such as calcium and sodium, are also metals. Elements toward the middle and left, such as mercury, are also metals having metal-like properties, such as shininess, as seen in this aluminum foil, and are malleable, the ability to be shaped. Metals are also good conductors of electricity, such as that found in this electric fence. Generally speaking, metals also have a high density, as is the case with this piece of rapidly sinking lead. Magnesium, a metal commonly used to make airplanes, is in a specific family of metals called the alkaline earth metals, highlighted here in blue on the periodic table. The alkaline earth metals are a highly reactive group. For example, magnesium, seen here, brightly reacts when burned. Within the metals are the transition metals, seen here in green. They are less reactive than the first 2 groups of metals. There are many commonly used metals in the transition metals, including iron, used in making machinery and bridges, copper, used in wires and pipes, and tungsten, used in light bulbs. These shiny metals tend to be good conductors of electricity. Transition metals, such as iron, zinc, and cobalt, are also used to make colorful paints. The elements to the right of the staircase-like line in the periodic table are called the nonmetals. The nonmetals tend to have opposite properties from the metals. These elements tend to have a dull luster and are brittle, such as this sulfur. They have low densities and melt at lower temperatures. They do not conduct electricity well. One such family of nonmetals are the noble gases, highlighted here in light red. These elements are found in small amounts as gases in the Earth's atmosphere. Argon is the most common of the noble gases and makes up about 1% of the Earth's atmosphere. Many signs are made with inert gases, such as this neon-filled sign. The elements highlighted in orange, just to the right and left of the staircase line, are called metalloids because they have properties of both metals and nonmetals. Metalloids are solids that conduct heat and electricity better than nonmetals, but not as well as metals. Silicon is one such metalloid that is used in computers. It is valued in computers because it is a semiconductor, meaning it is somewhere between a conductor and an insulator of electricity. We have explored just a small amount of the information found on the periodic table. Next time you get a chance, spend some time exploring the periodic table. You will be surprised at the amount of interesting facts you will learn. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1. Atomic refers to the arrangement and number of smaller particles in an atom.
Okay, so that's the end of the video. You have your worksheet to answer the questions from, okay? Let's make sure that you get that turned in. And the answers will be posted really soon, so that way you can check your worksheet, okay? All right, have a good weekend. I will see you next week on Tuesday.